Welcome back, Algebra Express. We are in Marecek 8.5, or it says 8.5. We are in Marecek. This is called a Marecek 8.5b. We are still in Marecek Chapter 8. We're dancing around 8.1, 8.2, and 8.5. So we're continuing our talk about radicals. So this chapter is titled More with Radicals. We're going to start talking about cube roots first. So the cube root, and for some reason it dropped off a symbol here. So if we do the cube root of a, C is a cube root of a if we can cube C and end up with a. So this is very similar to our definition of a square root, except for 2. Now we have 3. So now we have 3 things being multiplied that we need to look for. So if we look at 8, I want to break 8 apart into its factors. So I talked about this. I can do a 2 and 4, 2 and 2 if I want to break 8 apart. So 8 would be 2 times 2 times 2. And this, the indices on my radical. The number 3 is telling me how large the group needs to be. So when we did squares, we would take out groups of 2 and leave the single things alone. So now we're going to look for groups of 3. So if it's a group of 3, I can bring this group out and it comes out once. So I have a 2 here. I have nothing left underneath this radical. So this is equal to 2. We want to break 27 down the same way. 27 is not divisible by 2, but it is divisible by 3. So 3 and 9 will give you that, and we got 3 and 3. So you might notice 27 is 3 times 3 times 3. And we look for groups of 3. So I have one group of 3. I'm bringing this out. So I bring that out. The 3 is coming outside the radical. And this should be equal to 3. So now we have a minus 64. So I want to just look and break apart 64 first. This is what? 2 and 32. 2 and 16, 2 and 8, 2 and 4, 2 and 2. So I'm going to have 1, 2, 3, 4, 5, 6 2's total. Okay. And we want to think about this negative number. And so when you have a cube root, when we had a square root, there weren't 2 things that could multiply to a negative. But now I want to think about, and maybe think about this separately, if I just do the cube root of a minus 1. So what happens to a cube root of a minus 1? I'm looking for 3 things that multiply to a minus 1. If we think about the cube root, if we have 3 negatives, overall that is going to be a negative. So this is the same thing. And if I have a group of 3, I can always bring it out. So negatives, when we have cube roots, when we have 5th roots, when we have 7th roots, when we have an odd number of roots, we can always bring out the negative. When you have even roots, like square roots, quarter roots, 4th roots, 6 roots, 8 roots, you're going to have that issue of not being able to pull out a negative, because 2 things multiplying together are never going to be a negative. But when we get 3 or we get an odd number, it is negative. We can pull out the negative. So I also want to count for the negative 1. So if I'm looking for groups of 3, I'm looking here. I have a group of 2. I have a group of 2's, and then I have the negative that I have to account for. If you want to draw, I guess, -1 times -1 times -1 here 3 times, you can absolutely do that and circle 3 negatives if you wanted to. So I have a 2 that I'm pulling out, I have a 2 that I'm pulling out, and I have to pull out the negative. So overall, if I do 2 times 2 and a negative, this should be a -4. And if we do -4 times -4 times -4, we can get back to 64. Okay, so 2 times 2 times 2, this should give you, so we're going to fill out some perfect cubes. So these all came out evenly. They came out as an even number. There was nothing left underneath the radical. If you want to write out groups like this is a tried and true sort of way to get there. If you know your perfect cubes, if you knew that the cube root of 8 was 2 and the cube root of 27 was 3, I would not expect you to write out this grouping every single time. Right? You could probably jump and start recognizing these perfect cube roots. And 5 cubed is 5 times 5 is 25 times another 5 would be $1.25. So much like we did the square roots, if you can recognize these perfect cubes, you might be able to use this to your advantage. But like word of caution, you have to really pay attention to whether there's a cube or if it's a square root. Okay. So we want to do powers of x now. So we're raising exponents to exponents. So the rule is that we multiply exponents. So this is x to the 2 times 3 is 6. This is x to the 3 times 3 is 9. X to the 3 times 4 is 12. So we get things that look like 3, 6, 9, 12 if we're talking about cubes. What is true of your exponent? If x to the n is a perfect cube, we're looking like 3, 6, 9, 12. It's going to be a multiple of 3. And if you want to do this, we can do this the long way, I guess, first. So we want to do the cube root of x times x times x. We're looking for groups of 3. We circle a group of 3. It's going to come out once. We could do the same sort of thing here. 9, 10, 11, 12. Okay, whew. A lot of A's. And we're circling groups of 3. So 1, I did it right. 4. I got 4 groups there. I got A times A times A times A. So I circle groups of 3. They come out as 1. 1, 2, 3, 4. I have A to the 4th power. And so we did it the long way. And I did it the long way because I don't want to have to keep doing it the long way. You might notice to go from this power to this power, we're multiplying by 3. And so if we want to go the other way and do a cube root, we're going to divide by 3. So if we do 3 divided by 3, that's going to give me x to the 1st power. If I do 12 divided by 3, that's going to give me a to the 4th power. This is a lot like division. Okay. So the next thing they're going over is this product property of radicals. So if the root of a, the nth root of a, and the nth root of b are real numbers, and n is greater than or equal to 2, is an integer, then the nth root of a and the nth root of b is equal to the nth root of ab. So this is the same sort of thing we had with the sort of square root. If we have what, like 20, 4. 25 and 4. Like root 25, root 4. Might notice it's 5 times 2. Is the same thing as root 25 times 4, which is 100. So we could separate them under the radical for a square root. The same thing with a cube root. So we have something like cube root of 2. That's not something I'm going to be able to simplify. 4, but I can combine them, make something like the cube root of 8, which gives me 2. So I can do it with cube roots. I can do it with higher roots as well, is what this is trying to tell me. There's something they're kind of assuming for even roots, like a and b have to be positive numbers. If we're getting into imaginaries, we have to pluck out the i's first, right? So they're kind of dancing around that fact, I feel like. But it doesn't work so well with imaginary numbers, so probably note that. Rewrite the expression as a product of a perfect power and a remainder. Okay, so now we're simplifying these things. They are probably not going to come out evenly, is what this is telling me. So if I look at 54, I want to split up 54, find its factors. I'm looking at 54. I'm looking at what, 2 and 27. 27 is like 3 and 9, and 3 and 3. So I'm going to go ahead and do this. So this is like cube root of 2 times 3. The long way first, and then I'm going to like show you maybe a bit of a shortcut. What I have here is I'm looking for groups of 3. It's a cube root. I circled the group of 3. It's going to come out once. So this is coming out. I should have a 3 outside of my radical. It is a cube root. Don't forget to put your index. And there's still that single 2 guy left underneath there. Okay. That is one way you can do it. Another way you might be able to realize that this is the cube root of 2 and 27. So 2 times 27 will give us 54. You might notice that this is a perfect cube. So perfect cubes, I'm going to just go ahead and admit it. Like they are a bit harder, and they take me a second more to realize they're a cube root than they are a square root. If you get things higher, I'm probably not even going to recognize them most of the time. Fourth roots, I think maybe like 2 to the 4th is 16. That's probably about all I know. 3 to the 4th is probably 91. It's if you square a square, you get a 4th root. But things higher than that are definitely a lot more difficult. So, we have this cube root of 2. We have this cube root of 27. So if you recognize that this is a perfect cube, this is just the perfect cube of 3. This is 3 times the cube root of 2, or 3 cube root of 2, which is what we got previously. So my whole point before I went on a tangent was that the cube roots are definitely more difficult to recognize than the squares, or the perfect squares. I mean, the perfect cubes are more difficult to recognize than the perfect squares. I know my squares a lot better than I know my cubes. But we can always break this thing apart piece by piece. So if we look at 48, like 2 and 24, 2 and 12, 2 and 6, 2 and 3. So it looks like I have 4 2s and a 3. So doing the cube root of 48 is 1, 2, 3, 4. So I want to circle groups of 3. So I look 1, 2, 3, and this is going to come out once. So this is coming out as a 2. I still have a cube root of 2 times 3. And so this looks like 2. You might want to do a little bit of cleaning up with this if you can do it. So this is 2 times 3 is 6. Okay. Another way you might be able to do these, if you notice there is a 2, a perfect 2, which would be 8. Times 8, you can break it apart. You might be able to break this apart into 6 and 8. Recognize that this is a perfect cube. This is 2. And we're getting the same solution here. These are being multiplied. Okay, so now we want to look at this thing. So if I have y to the 5th under a cube root, so I do the cube root, and I write out my y 5 times. I'm looking for a cube root. I want to circle 3 of these things. I circle 3 of them, and I bring them out as 1. So I can bring out a single y. And I'm going to have a cube root. I still have 2 of these things remaining underneath here. So maybe a word of sort of caution. Like when we did square roots, we could only have 1 remaining. When we go to cube roots, we can have a remainder of 2. So if we divide by 3, we can have a remainder of 2. And there's still 2 underneath the cube root. We're not going to be able to factor any more out. There's not an even group of 3 here. So we can up our remainder by 1 now, I think. So 1 times 3 plus 2 will get you back to this 5. So that's why I kind of wrote the exponent. I'm probably not going to write the exponent this time. It's going to be like y cube root of. So which of the following, so this is kind of exactly like what we got with the square roots, but now they're doing it with cube roots, where they factor out more and more. We can factor out 3, we can factor out 6, factor out the largest number that you can. We go 3, 6, 9. Why can we not go to 12? Because we're only doing 11. Okay, so which of the above makes use of the largest perfect cube factor? It's this one on the end. How can you tell that a larger cube square factor cannot be taken out? Because the next one is 12, and we're only doing 11. 12 is bigger than 11. Okay. So we want to simplify this thing. So if you want to think about it like they're doing it here, that's fine. We can keep on going 3, 6, 9. We can take out 9, z to the 9th. And then do it. So what I'm going to probably do is just division. So if we think about 11 divided by 3, I can take out 3 with a remainder of 2. So if I'm doing this, I'm doing a cube root. I can take out 3. So 3 groups are coming out. And I'm going to have 2 remaining. And if you do it their way, you're going to get z to the 3rd right here for 9 divided by 3. And there's going to be a squared left over. And again, 3 with the remainder of 2 would look something like that. That's where these numbers are coming in here. And then this 3 that we divided by is like that radical. We're dividing these into groups of 3 is what we are doing. Okay, so now they gave us numbers, they gave us letters, variables, and so now we want to do numbers and letters. So, numbers and variables, we're doing cube roots. So 40, we want to look at 40. So if I start, think maybe looking at perfect cubes might help us. So if we're looking along here, whoa, where is that? There's the first page. We're looking along here at our perfect cubes. We're looking at 8, 27, 64, 125. Start with like the lowest 8 and 40. I think we can divide 40 into an 8 and 5. Instead of 40, I think I'm going to write the cube root of 8 and the cube root of 5. And I still have the cube root of x to the 7th. And the cube root of 8, that is an even cube root that I can take out. This is 2, this is the cube root of 5. And now I'm trying to figure this thing out over here. And so to figure this thing out, I'm going to divide 7 by 3. So I'm going to get 2, that's going to give me 6, and I'm going to have a remainder of 1. So I'm going to be able to take out 2 groups. And I'm going to have 1x that's remaining. And so now I do need to clean this up a little bit. Things outside the square root, I'm going to put with things outside the square root. So 2x squared is going to go out first. And things inside the square root, I'm going to use that property. I can combine things inside the square root with things inside the square root. So multiplying cube root of 5, cube root of x is going to be the cube root of 5x. So I know I'm probably using this property without saying it a whole lot, but we can take these things, we can separate them into sort of separate radicals, and then coming back, things that are in separate radicals, we can combine them under the same radical. So another sort of way to approach these is that things on the outside kind of get multiplied with things on the outside, things on the inside kind of get multiplied with things on the inside. And in a minute, we'll do division, and guess what? There's a sort of similar property. Things outside the radical can only get divided with things outside the radical. Things inside the radical can only get divided with things inside the radical. But we're going to look at this thing. We're looking at 128. So if you can notice a perfect square in there, it might save you a little bit of time. So I'm looking, I think 8 and let's do it. 8 will do it, but I think we can get 64. 128 divided by 64 is going to give me 2. So if we want to break this thing up, I can break this up into the cube root of 64 and the cube root of 2. Then I can do the cube root of x to the 11th. If I look here, the cube root of 64, that is a perfect root that we found on the previous page, was 4. I have the cube root of 2 and the cube root of x to the 11 divided by 3. So I'm thinking about 11 divided by 3. I'm going to get 3 out of there with the remainder of 2. So I'm doing x to the 3rd with the remainder of 2 underneath the radical still. So I'm doing 4x to the 3rd. The radicals still are 2 and an x squared. Okay, so let's suppose you know what 128 divided into. So if we do 2 and 64, 2 and 16, 2 and 8, 2 and 4, 2 and 2. So worst case scenario, we should be able to divide this thing out 2 by 2 by 2. If we do this, we get 1, 2, 3, 4, 5, 6, 7. There are 7 2s in there. 3, 6, 7. And we still have what, x to the 11th in there. And if you really wanted to, you could do these the same way that you do your variables. If you just wanted to write 2 to the 7th and x to the 11th, and you just want to divide things and get that sort of thing done with, you could absolutely do that. But I want to circle my groups so that people can see this. So we're going to go 3 here, 3 here. I'm going to pull out a 2 times 2 is what this is telling me. I have 1, 2 groups. I have 2 times 2 that I'm pulling out. I have 3, a cube root of 2. And now I want to deal with this x to the 11th. 11 divided by 3 is going to give me, I've already done this, x to the 3rd with the remainder of x squared on the outside. That is a 3. Let's get it better. So this should be the same solution of the 4x squared cube root of 2x to the 3rd that we found previously. So either way you can go about this. If you notice the perfect cubes, you can go for the perfect cubes. If not, you might have to spend a little bit more time. These are smaller numbers, so these are definitely maybe easier to notice perfect cubes in. Probably 27 is a really easy thing to notice a perfect cube in because it is a perfect cube. So we can think about this as the cube root of 27 and the cube root of x to the 14th. Separately, this is just 3. Now we're doing 14 divided by 3. So 14 divided by 3, I believe it's going to give me 4, it's going to give me 12, and I'm going to have a remainder of 2. So I want to pull out an x to the 4th power, and underneath my cube root, I'm going to have an x to the 2nd power. And you can do some checks sometimes. 4 times 3 is going to give me 12, plus 2 is going to give me back the 14 underneath. So now I'm looking at this last one over here. Cube root of 48, x to the 15th. So the cube root of 48, if you can recognize an even cube in this thing, it might benefit you. The first even cube is 8. So 8 and 6 will give me it. And I'm looking also at the cube root of x to the 15th. And so the cube root of 8 is going to give me 2. I have a cube root of 6. And now I'm looking at this thing, x to the 15th divided by 3. 15 divided by 3 is going to give me an even 5. And I'm going to have a remainder of 0. So what this is telling me is that I'm going to get 5 groups of x coming out. And I don't have anything left underneath the radical. I don't need to write that radical there anymore. So the other thing that you might want to kind of sort of check is this cube root of 6. Can we pull anything else out of this cube root of 6? Well, if I'm looking at cube root of 6, I'm looking at cube root of, we can think about this as 2 times 3. Those are 2 primes. They are separate. There's no way I'm going to get a group of 3 out of 6. So there's no way I'm circling 3 of the same thing over here. So cube root of 6 is fully simplified as much as we can simplify it. So I might rearrange this just a little bit to put 2x to the 5th out in front of the cube root of 6. Okay. We got a little bit more practice. Ooh. So hopefully try doing these. So you might look at these and say, hey, isn't it the same problem? And no, it is not the same problem. This has an index of 3. This does not have an index. So if this does not have an index, what the heck is that thing? It's a square root. So if you don't see a number, you can kind of always assume that what we're doing are square roots, the number there is going to be 2. Okay. This, again, we want to factor things. So it doesn't really matter how we do things. We're going to factor the number anyway. So 54 is 2 and 27. And I think we did this already today. 3 and 9 and 3 and 3. I feel like I wrote that out once today already. Okay, so 2 times 3 times 3 times 3 is 54. So if we're doing a square root, times 3 times 3 times 3, 4, and I have an x to the 11. So for this thing, what am I doing? What is my approach to square roots? I want to circle groups of 2. So groups of 2 are going to come out as 1. And the other thing is I have this thing to worry about. So 11, what am I going to do with that? 11, when I'm doing square roots, I'm going to divide by 2. So this is going to give me 3. X to the 11th, I'm going to do x to the 5th is going to give me 10, and I'm going to have 1 remaining. So I have 2 times 3 is going to give me 6, and I have a single x remaining underneath. Okay. So now we are doing cube roots. It is the same number. 2 times 3 times 3 times 3. And I do x to the 11. So if we circle a group of 3, we can circle 3 3s. They're going to come out once. This is 11 divided by 3. So 11 divided by 3 is going to give me 3, will give me 9, and I will have a remainder of 2 underneath. So I now need to look at my numbers is 2. So the last section we're going to deal with dividing by radicals and how to simplify radicals that are in the denominator. So they give you this quotient property of radicals. So if we have a cube root, the nth root of a and the nth root of b, and it's larger than a square root, then if we're doing a square root, and we had this sort of similar property last time when we did a square root of, I don't remember what it was, like 25 over 49, I think it might have been something like that. If we have a square root of 25 over 49, we can look at that as the square root of 25 over the square root of 49. We could look at that as 5/7. Or we could look at this thing kind of separately as two separate fractions. Either way, you should be getting 5/7 out of this thing. So we can distribute that radical across the numerator and denominator if it's of a fraction. So if we look at something like the square root of 3/5, we typically do not like to have fractions of or radicals of fractions. We don't like to have fractions in our radicals, I think is was the direction I was going to go with that. So we try to get rid of fractions in radicals if we see them. We try to get rid of fractions in the denominator if we see them. So these would look like radicals of fractions, radicals in the denominator, and we get two of the same kind of example, right? So square root of 3/5. So in order to solve this sort of problem of having a radical of a fraction, we have to distribute that radical with the property I was just talking about. If we have radical 3/5, it's sort of like radical 3 over radical 5. Okay. And so now I'm looking at this thing and I want to simplify this. I don't want a radical in the denominator. So this is one of the sorts of things where I'm going to have to multiply this by a big fancy 1 to get an equivalent sort of fraction. So I want to multiply something by the square root of 5. That's going to get rid of it. And so I already have 1 5 underneath the square root. And so in order to complete that, I need another 5 under there so that I can get 2 5s under there. And so if I'm doing a square root of 5 here, I have to do a square root of 5 here. And so the square root of 3 times the square root of 5 is the square root of 3 times 5, which is the square root of 15 up here. And down here is the square root of 5 times the square root of 5. If you want to write them separately, still, I guess that's okay. But I'm just going to say that's the square root of 25. Square root of 15, that's a 3 and a 5. There's no way I'm simplifying the square root of 15. But square root of 25, if I did things correctly, it should be a perfect square. I can pull out the 5 now. So square root of 25 is 5. So now we're looking here, square root of 15 over 5, and we're asking ourselves, can we do anything to simplify this? And I know what you're thinking. 15 divided, no, don't go dividing this thing. Sort of like I was talking about, if underneath the radical, this is not underneath the radical. So this we cannot divide. So if we had something, let's give something. And let's do 6 squared. Yeah, this will work. So if we had something like this, it's a little more complicated, but I think we'll get at the point. So if we had 10 square root of 6 over 5 square root of 2, what we want to do is we want to divide things that are under a radical with things that are under radical. We want to divide things that are not under radical with things that are not under radical. We want to keep those things separate when we do multiplication and division. And so when we do this, we can separate these things with the rule of multiplying fractions that we kind of sort of know. This is just 10 over 5. We can divide those things. So things outside the radical, I think it's pretty obvious why we can divide them. This is the rule that we just employed. If we have a square root of a fraction, we can write the square root in the numerator and the denominator. But if we have a square root in the numerator and denominator, we can also write this as a square root of a fraction. So this rule is coming back in this sort of play here. We can simplify things like this. And again, the rule is divide things outside the radical with things outside the radical. 10 over 5 will give you 2. 6 divided by 2 will give you a 3 remaining under the radical. So you got to keep them under the radical. So that is fully simplified. Don't try to divide those things. That does not work. This thing, we have a square root of 2. So we want to get rid of this radical on the bottom. We have 1, 2 down there already. So since we have 1, 2 down here already, we need another square root of 2 to complete this thing off. So since we need another square root of 2 on the bottom, we need 1 on top as well. So on top, I have 5 times the square root of 2. So this is, again, like I'm saying, if you have to write a 1 in front of this radical 2, you can write a 1. It's not going to change it. But the thing we want to do is multiply. So 5 times the square root of 2 is just 5 the square root of 2. So we don't multiply things outside the radical with things inside the radical. They stay separate. We multiply things inside the radical with things inside the radical. So square root of 2 times the square root of 2 is like the square root of 4. We did all this so that we have an even root of 2 on the bottom. So now I'm trying to see if this thing is fully simplified. So if I wanted, I could do 5 divided by 2. It gives me 2.5, right? It's not going to clean up any. So the other thing is the square root of 2. You don't want to be dividing this with anything down here because all we have is that 2. We don't have anything underneath the radical. So there's no radical to divide this by. Okay. So square root of 4 over 75. So this again is the same approach to the previous one. We have a square root of a fraction. This is like the square root of the numerator over the square root of the denominator. So the square root of 4, that's an even 2. This thing, if you wanted to try to multiply by your 1 and multiply by square root of 75, you could absolutely do that. But you're going to end up doing just a little bit more work than what you would do if you clean this up first. So if this is the square root of 75, I'm thinking there's a 25 in there, which is an even root. 25 and 3. 5 the square root of 3. And so now I'm thinking I want to, not equals. I want to multiply this by something. And I want to multiply this by something so that there is no radical down here. So the radical that I have down here is a square root of 3. So if I want to get rid of a square root of 3, and I already have one, I need one more. 2 times the square root of 3 is 2 the square root of 3. 5 times the square root of 3 times the square root of 3 is like 5 the square root of 9. So we can combine the 3 and the 3. And we're doing that because it is an even root. So this like 5 square root of 3 is like 5 times 3 of what's happening down here, 2 square root of 3. So this looks like 2 over 15, square root of 3 over 15. What are you looking to? There we go. Okay, the last one, they're throwing in a variable now, but it's not even underneath the radical. So again, if you can simplify things in the beginning, it might help. I have x over 98. So if I do 2 in 49 will give me it. And 49 is already an even root. So I I'm just going to go with 2 and 49. So if I separate this into 2 and 49, what this is actually doing is x, and I have 7 square root of 2. I'm looking here, I want to get rid of my radical in the denominator. I have 1 square root of 2. If I want to get rid of square root of 2 and I have 1 of them, I'm going to need 1 more. What this looks like to me is I have an x, I have a square root of 2 on top. I have 7, and I have square root of 2 times square root of 2. I did this to combine it as a square root of 4. So that is 7 times 2 on the bottom, so x square root of 2 over 14. And that is the final problem we're doing in this section. So I will see y'all soon. Take care.